Anthony. So what is it? Is it 1 byte or?
I know, I'm sorry, I take it back. It's not 1 byte. It's 32 bytes. The buffer is 32 bytes. I was looking at the wrong program when I said that.
So what do you mean you're looking at the wrong way? Is that the left one? The left one is what?
This is the user space driver.
Oh, this one.
Yeah, so I looked at it
Anthony,
quickly.
you need
and
to
I
be
said that.
organized because I don't know what you know. I'm trying to learn what you did. So what is it that you're trying to show here?
Okay, what I'm trying to show.
Homework 10 was byte based and presentation requirement was array based. So
Right.
why you not clear on what this is a presentation that you should be prepared for, right? You're going from one to another, not knowing exactly what you want to present. It seems like to me you're trying to learn the presentation. But in any case, so just walk it through, you know, and
Right. So my example driver program, which I misspoke, I was clicked on the wrong one, will open the file. It will seek set, so seek from the beginning. So we're going to increment the pointer, and we should move the pointer for each of these iterations, and we'll write a single character to the buffer. So if we scroll back in the demessage window to the beginning, we can see that on each read, we display the contents of the buffer in the kernel print. So we're putting B on the buffer in the kernel. So the array looks like B, followed by the rest of the letters. So the character B just stands for beginning. So as we come down here, we can see what we've done through this loop. We've put B in each position on the array. So of course, B is the second character, so it's not going to look like anything there. In the third case, the fourth case, the fifth, and we iterate through, pushing the cursor one character over until we've filled the entire buffer up with the letter B. Okay, so at this point, we filled the buffer with the letter B. The second iteration loop here, we'll do the same thing, but we'll work with the buffer from the end. I'm sorry, we'll work with the buffer from the current position, not the end. So it sets it back to the beginning and it moves it over one. And it writes C as we go through. And C again is for current. Okay. And then we do the same operation once more for the cursor from the end. So if you see the E's now are written from the last character, I'm sorry, last position towards the beginning of the array. So as I scroll down, you see the E's are moving left. This is because they're getting placed with the seek operating from the back. Let me get to the end of this. And the last part of this program is to allow you to just enter a character and it will get placed on the array using seek set and incrementing the value of 1. So whatever I type will just be put in the new position on the array. I'll type an H here. Let me see there's an H. I'll type an R. Let me see now there's an R. And it'll continue until the counter reaches 26, and then the counter will just loop around and we'll write back from the beginning. So it's a little program that demonstrates seek from the beginning, seek from the end, and seek from the current cursor. Okay, so that again was the dev memory version. I have the proc version too. Do you want me to show that?
Can I see your user space program?
Yeah.
This is the, okay, that's.
Which part do you want to see?
Go down, please. Could you go down? Down.
This is the bottom of it.
Yeah, go up. Yeah.
You want me to go to the top?
Yeah, that's okay. See, just walk. Just go up a little. Let me see a few things. Could you go up? Up.
To the top?
Yeah, actually go to the top. Yeah.
Yeah.
Yeah. So I'm gonna see. Okay, could you go down? So, okay, so let me ask you something. Okay, so you're going from I equal to 0, I less than 27. And then at each case, you're doing opening up a device. Why are you doing that?
So I chose to open and close the device because I was getting a issue with, I don't know if it was the buffer or something else, but I wasn't able to continuously read and write to it. So the easiest thing to do was just open and close the file pointer for each iteration.
But, but you know that's not a good programming, right?
I know it's not a good approach. I think I was having some problems with the Linux kernel I'm using, and it took a while to get it working this way. So this is for the sake of demoing the functionality of the seek, I chose to just stick with this.
So if you have to do this 10,000 times, you're going to open and close the kernel?
I mean, for the sake of this demo, yes, but not in actual practice.
Your approach is not, part of it is for you to learn some programming skills. And I just I'm just telling you, don't, I'm just saying that that's not a good practice. That's all I'm saying.
I agree with you.
Saying,
for the sake of the demo, this is what I got to work, so I stuck with it.
Kernel and closing. What is going to affect the performance, But in any case, it's not okay. So that's one thing. Then you go outside this loop. Then you open up the device again, and so now.
So in this step, I just reset the pointer back to the beginning, so I could do the C current.
Then you do the same thing for.
I do it between each one, so I can just get it.
So what is the first loop does, and then what is the difference with the second loop? Because you're doing the same thing for the second one as well, right?
Right. So if we look at the difference, where is the seek? So the first one has seek set. The second one has seek cur. And the third one has seek end. So I was just trying to demonstrate the use of the different seeks by moving a character back and forth in the.
Could you, okay, so could you continue with your presentation?
Yes. Do you want to see the dev version?
That's the homework 10, so that's okay. This is presentation.
Okay. I wasn't actually clear which one it was, so I have both of them. But that's all right.
But you have to do some time management. You got to move on.
All right, I'm going to close this for 1 second and just move it to the other monitor. Can you see that?
I don't. I still see what you had before.
Okay. How about now?
Yes. Yes.
Yeah. Okay.
Could you remove the left? I don't. Okay. So is that the program associated with this?
Yes.
Okay. Go ahead.
Okay. So the first program is pretty simple and straightforward. It just echoes text to the terminal. The additional portions I want to talk about, I just picked from the list: process life cycle. CPU instruction execution cycle. Sorry, I'm gonna just drink some water. in the CPU registers. This is a flow chart for the program, and I'll just run the program. The program will print the error, print the welcome message. While we're in the loop, if we enter a string, it'll get echoed back to us, unless we enter the escape key, in which case the program will close. Okay, so that's here. That's good? So the process life cycle, I don't want to go through all the details of how this works in general, but for this program specifically, we'll see that the program is loaded into memory and the PCB is created for it. The process is then admitted into the ready state, which we'll see here. The scheduler picks up the process, moves it to running, and it starts processing. The print message 1 happens, and then we have an IO event.
Could you go back up? Could you go back up
To,
yeah, I want to see the beginning. So what is this program does? Let me see so it's a program that does the welcome message and then a loop, not, okay. And so while you do a scan and then you do a buffer break, print, text entered, so you typing from the command line, printing the message, is that what you're saying, right? The
yes,
scan.
hello, type in hello, it's echoed back. If I hit the escape key and enter that character, then we exit the program.
Yes. Could you go down, go now, next.
Okay, so the next part is,
So, okay, so now you want to process, like, what is this now? What is it you're trying, scenario 1?
yeah, this is
process
scenario 1,
Okay,
number 24, the process lifecycle diagram.
yes,
Okay, so this program, as it runs through, so the part I got to is we print the message, and then we have an IO event where we have the scanf. So the process will get put into the IO waiting queue. It'll wait until we enter some keyboard command. The event will register. The process will be put back into ready, where the scheduler will then pick it back up again and then execute it. And we will run through the rest of the execution like this. Until, of course, we hit escape, and then the program will be moved from running to terminated.
okay,
Okay. Part of the code usage for this is the struct for the PCB. One of the entries for the PCB is the state. And so as we move through, the PCB will updated with task running, task wait, or whichever one of the states.
So what you have is that you've hello program 1. So that's the process, and then you have a scanf. That is the system call. Okay.
Yeah.
Yes. Okay. And then so each process you process control block struct. What is?
Yeah. So I'm just showing the process control block, the struct for it, and the fact that it's got an entry for the state. So I wanted to just show that as the process moves between the queue states, the state will be updated. For example, from task running to task wait, depending on what queue state it's in.
Okay.
Okay.
So you just okay. So I just want to make sure the context is correct. That's all. I mean, so you have a PCB data structure. So you just, right?
Yep.
You have you're presenting PCB struct. That is the, so it's got a, so you have a struct scheduler entry, which is, okay, scheduling information. it's got a state.
Yeah, I was just trying to
Yeah,
demonstrate
what
here,
about-
show that the PCB has a state. So as it moves between the queues, the state will just be updated. So as far as things that to be implemented in the operating system that I can do for this section, you can implement some code that changes the PCB state as it moves between the queues. That's all I was trying to show here.
Okay.
Okay.
Yeah, so you had the data structure showing a number of things, and yes, I just want to, but the context is really the state.
For right now it's the state. Yep.
Yes.
Okay.
Okay, go ahead.
Okay. So another scenario to discuss for this program is the CPU instruction fetch cycle. A quick view of it is we have the registers and the control unit, the ALU or floating point, and the memory. What we're going to do is, based on the value in the counter, pull the memory instruction at that address into the.
But I don't see anything. Can you?
You can't see this?
Yeah, it's very hard. Okay.
All right, you're going to make it bigger?
Yeah.
Is that better?
Yeah.
Okay.
So,
Right, so based on-
once again, this is a scenario, right?
This is scenario number 2, the
Okay.
CPU instruction fetch cycle.
The idea is that you want to, so your program is just scanning an input and then print it out, right?
Correct.
And then you're trying to show what happens at the CPU.
Yeah, I want to demonstrate just a use of the CPU fetch cycle for this program. This is just a block showing what it is. If we look at the specific code for this, a line for this, for example, the print statement, enter escape to exit. In the C code, this looks like this. In the assembly, it gets created into the EAQ, LC1, and then a call statement. So the execution is going to do the same thing. The PC is going to point to this memory location. This instruction is going to get pulled out of memory. Again, it's the EAQ. It's going to get decoded and then executed. So we're going to move the value of RDI into RIP. The PC is updated again, which points now to this instruction here. Call gets pulled out into the memory register. And then we're going to...
What does that call do?
This call calls the function puts, which is going to put this value out to the terminal.
Yes, okay.
So basically, these are the 2 steps in assembly that are created from this or generated from this printf statement.
Yes. Okay, so yes, okay, so that's the, yeah, that's okay.
Okay.
Yeah, and then go back to the registers. Go back to the top. This figure here.
Yeah.
So, so program counter is 1, you saying?
I mean, I just threw a number in there. I don't know what the program counter is actually for that execution, but it's going to point to this memory address.
Anthony, you need to. You're assuming that we know. I need to walk it through that. Make sure you know what.
Okay. Well, I didn't want to teach too much.
You're
is
putting
what
a
I'm trying
code
to get
in
away
the
from.
program counter of 1, and then now you're saying you don't know why you're putting it there.
Okay. I'm sorry. This doesn't illustrate that.
Now explain to me, Anthony. Just a second.
Okay.
Anthony, explain to me what is this diagram is trying to show.
Okay. This diagram shows if we want to use PC counter 1, we're going to fetch the memory location at 1 here, which is the instruction move AL6. So we'll take this instruction, we'll move it to the memory data register. The control unit will then decode what this is. It's a move. And then the control unit will signal to the processor to do the task, which in this case is move 6 to the AL register. and that will be one cycle. We'll then increment the PC, which would then be 2. We'll do the same process and we'll fetch the move instruction, we'll decode it, and then we'll move 7 into BL. And then whatever the next task would be, maybe it's add, subtract, you know, there's no third instruction here at the moment. So it will be performed, whatever it is. I had this just to demonstrate
But
the system.
just a second, Anthony.
Yep.
Part of this, you can't just say things but you have to have a goal, okay? You have a line of code only, right? You're saying the next thing you showed is that one printf, right?
Mhm.
That's and then you showed the assembly code for that.
Yes.
So you went from, this is the assembly instruction for what? And then the next one you're showing assembly instruction for what? Why is it, you see,
For these two?
basically compile the code, link it, and then now you can have assembler code and then machine code. So you're presenting a printf, right? And you're showing that your program 1.c printf, and then you say that you're showing the set of instructions, assembly instructions. It's just any assembly, that's fine. But then in here, go back up. You see in here, you have a picture. What is the intent of this? I mean, you're going from one, it's not, I don't see an order to this. All I see is that you have a program that has, you want to present the one line of a printf, right? And so, and then your scenario is 2. You're trying to show the architecture of the what the registers would do in this thing. That's what your scenario is. And then so this you changed something.
What's that?
You changed something, I think,
I don't think so.
on the diagram.
No.
Okay, all right. So move 6 to AL and then 7 to base register on the lower part. And then, okay, so I'm just trying to understand why, you know, could you go back up again? Your scenario is to CPU instructions execution cycle, fetch, decode, and execute. So
Correct.
fetching, it takes those steps 1 through 4, and then decode is 5, and then execute is 6. Okay, and then you have this diagram here is really losing me. All right.
Okay, so I didn't want to walk through this because I didn't want to just teach what was happening. I had the diagram as a reference, and then the relevant code section that I wanted to explain from the program example is this here. So I guess I could have put those values
Are you
into
saying that you didn't
this.
mean to present this? Is that what you're saying? The diagram?
I mean, I have it here so
Because
I can
you have,
reference it.
yes, you're trying to show the process execution, fetch, decode, and execute. And then you throw this diagram in there. And then the next thing is that you're showing assembly code for the print function. So, okay, continue, please.
Would you rather I have not included any of this stuff
I'm just
here?
saying, I'm
Just
not
gone
saying,
with this?
it's your work. I'm not saying, I'm just saying you're presenting this, right? It looks like you're losing the connection from the first and the second by throwing that diagram. Because if you're saying go back up, you said fetch a step, 4 steps, decode is 1 and execute. Is that saying when the execute happens, the control unit signals the appropriate component to execute the instruction? The control unit, LLU doing, and then memory, and then, all right. No, I think it's fine as long as you could have described it.
Okay, I should have, but again, I was
mean-
trying to not teach and just do the relevant example from the work. I'll read everything I have for now on, because I'm afraid it's a little too teachy and not demonstrative enough, though.
Yeah, but I don't know. The context of teaching is not appropriate here, because you just you're putting something related to. Could you go back up again? You're just throwing a diagram in there. It's not teaching. So you know you say you have to say what this diagram does. So you have a memory, you have LLU, and you have a control block, control unit. And then this other one, and that you have, you know, and the first thing is program counter is 1. Okay, I think, you know, it's not teaching. It's just that you're not prepared to present that happening. But go ahead and continue, please.
Okay. And the third scenario is the CPU registers. For this, I took the program and I generated the file where I could see the machine registers. So the while one instruction is converted into these 3 instructions. And then the fourth is the destination that the code will jump to. So what while one becomes is move, and we're going to move the EAX, I'm sorry, we're going to move the address pointed to by the second parameter into the EAX register. And that's one of the registers we saw above. We're then going to do a compare with AL, and AL is the low byte of the EAX register with the value 1. And then the next instruction says jump if equals. So we're going to jump to the memory address 127D. 127D is a no-op. So basically, we are in a while one, we expect it to continue. So this is saying continue to the next instruction, no-op, and continue processing the rest of the code. What we would have had here, if it was not equal, would be some jump to something else.
Could you go back on this one, scenario 3? So scenario 3, what he's trying to show is that what is that he's trying to show with the scenario 3? CPU registers, how the CPU registers work?
Yeah, demonstrating the use of the CPU registers.
Yes. So you have an example for use of CPU registers. So that's the assembly instructions.
Yes.
What do you think is that? What do you think the interrupt happens when the interrupt happens?
Which interrupt?
You're setting up all the registers, and you're doing. At some point, you have to. What do you think the interrupt happens?
When you say interrupt, which interrupt are you referring to?
I'm just trying to refer to this code. I'm asking you, where do you think the interrupt happens? Because it is through the interrupt that you're telling the CPU to execute. You're setting up all these registers, each one has its own thing. And
Right.
then at some point you have to make an interrupt telling CPU to execute.
Right. Well, so first we have the move command, which sets up the register. Then we have the compare command, and then we have the jump command. So this is going to be the actual interrupt that moves the.
Where is that? Where is that? Yes. Where is that? Where is that?
Right here.
Well, so it's going to jump in, jump if it called, right?
Yes.
To 127. That's what. So that's the interrupt is going to happen. And so what is the, okay, so what is the next one? Next thing. You're saying in this instruction, we see you have, so the next set of instructions. Okay, how, I'm asking you. So now you have so initially you had starting at line 174. Okay. Anthony, you're doing the presentation, okay?
I thought you were asking me a
You're not making
question.
it easy for me to follow. What is the set of the next set of instructions that you have? Move Z, and then you, so you see, so what is the next set of instructions intend to do?
Yeah, you're saying next, but you're saying next in reference to
Because
what?
you're doing the same thing. You say, you see at the top, you say while one becomes this line in from program, right?
Yeah,
And then starting at 174. And then you walk through those four instructions. Then next you say, in this instruction, we see what? Okay, you're trying to explain that. Is that what you're doing?
I'm,
You're trying, because it's the same instructions.
yeah, this is an explanation of these up here.
You're trying to explain, move the value from, right?
Yeah, I thought I walked through it.
You did, but you see what I'm saying? You have two set of the same instructions.
Well, this is the code that I copied, and this is breaking out each of the lines and giving an explanation of the line.
Okay.
So move
But
is the command. These are the parameters, and this is a description of what the command does.
yes, but yes.
All right, you're just saying it's confusing
sure,
the way it's
I
listed?
wasn't sure. That's was just asking. You know, you could have just done the second set of instructions with explanation. But go on, move on, please.
Okay. Program 2, I'm just going to move this over for a minute and I'll make it back. Is a simple file open, write, close program. If I run program 2, I can enter a word. Hello. Let me just make this. I'll put in hi. And we create a file called program2.txt, and it's got the contents of the file here. The flow chart shows us.
Just walk through the workflow chart.
Okay, so the program starts.
Is this this is the second program? Is doing the same thing. Welcome message, and text the user input, open program text. And what is the difference between this and the first one?
This one creates a file and writes to the file on disk.
That's fine. Okay.
Okay, so opens the file pointer is null, print an error exit. If it's not null, write the entered string to the file.
That's fine.
Okay.
Go ahead.
So the first scenario I want to talk about is the superblock inode data block file control block file table. Something I think applicable.
One thing. You went to scenario 2. Okay, could you go back up?
Did I go to scenario 2? Oh,
You go
it's
back.
just listed wrong. I'm sorry.
Okay.
So I'm going to change this now.
So let's walk it through. Scenario 1 is you want to talk about the file system. So what is scenario 2 now? You change the numbering. Let me see scenario 2.
Well, this is the one that should be
You
first.
just changed it. They changed the numbers, right?
Yeah, I just changed the number.
So tell me, I just want to know, maybe you had an order in your mind.
Yeah, I'm sorry. I should have changed the number earlier. This was the order that was in my mind.
Okay, so your scenario 1 is the super block, and then scenario 2 is what now? Let me read it.
File system layout.
Layout map. You see, it looks like in terms of presentation order, you intended to do the reverse, right? Go ahead.
No, I intended to do this, and then I intend to do the file system maps to disk, and then support file system layout.
Okay, fine.
Okay. So in our program, we want to create a file called program2.txt. The first step is calling fopen in our program. When fopen is called, a new file control block or inode is created for this file. The virtual file system will take this call and create a new inode, returning the inode number. This will look something like inode create. And the function call can look something like this. And this is actually a snip from the simple file system. We'll locate a free block. And then we'll return this block to the system when we create a new file, and it'll be associated with the rest of the metadata. When create is called, an available inode will be taken.
What is an inode?
The inode is the entry in the inode table for every file. It holds the metadata for.
You said in a long thing. An inode describes the file.
Yes.
Everything about the file, and then you have a table because you have many inodes. Each inode is for a file.
So what this is going to do is locate a free inode and return it to the system.
Let me ask you something. When you're creating inodes, how does that? Is it based on a file? Like if you're creating files and then removing files, what happens to the inodes? The
inodes should be created already and formatted at the beginning of the disk format.
Yes, so, that's it. That's good. Thank you. Go next.
Okay, so we're going to allocate one of the free inodes to the new file and return it with a file pointer that can be used in the system. Okay, so the second scenario is OS file system maps to disk layout. So create a system to map a virtual file system to the hard disk. The file system maps a virtual file system to the hard disk space. The file organizational module is responsible for associating items in the virtual system with their location on disk. In our example program, when we have opened and created the file on disk, the user program has been returned a pointer to that file. The next user call that interacts with the file is fprint. This will make a call into the system to write. Since the data is only a few characters of text, this data will be able to be stored in a direct data block on the inode itself. The block pointed to by the direct block will be addressed by the hard drive driver. And then I'm just saying chances are that this will be stored in the buffer before it's actually written. And then the file close will actually flush it out to the disk.
Okay, once again, I want to go back. So, you know, what do you think? Some of these things is you should have worked on some diagrams, but that's okay. Go ahead.
I did want to have more diagrams. I just didn't have time to draw them, which is why I was asking if I could copy them from the book.
Well, you could have done it on the paper, right? Instead, you just copy the text. Well, how long is going to take to get an idea and write it on the paper?
Yeah, you're right.
It takes more time to use a tool to develop diagram, but writing it on a hand. After all those exercises, handwriting, quizzes, homework, no, home quizzes, it takes how long it takes to write diagram what you just said. Okay, part of this exercise is for you to learn. If you do some cheating in real world, it is not good, okay? But go ahead, continue.
Okay, so scenario 3, support file systems, IO operations for hard disk and drivers. So we can create a system to handle talking to the hard drive device drivers. The kernel interacts with the hardware, like the hardware drive through the device driver. The hard drive controller is a block device. As mentioned above, the virtual file system interacts with the disk by mapping the virtual blocks to ones associated with ones on the disk. When the disk write is initiated, the hard drive driver makes a request to the drive for the data at the location. The process is put in IO wait. the drive collects the data, and when it is ready, an interrupt is triggered to let the system know that the data is ready. The process is then scheduled on the IO queue, and when it starts again, when it returns, the process can continue. In this case, the process is complete and exits.
Okay. Go ahead.
Okay. So program 3 is one of the socket servers that we used in an example in the homework. It's just going to start. It's going to wait and accept. Let me get everything yet. An incoming socket request, and then it's going to make a connection, and then it's going to print whatever is entered on it to the terminal, and then it's going to exit. So if I connect to it on port 8080 and I just type a message like hello, we see that the message was sent to the socket, and then the message from the server, hello message, hello from server, is sent back to the client, and the program is closed.
So you socket programming. Okay, so
Okay.
3 scenarios. So program 3. Okay, so
Yeah. So for this, there's provide method to service IO requests with implementation details, compile time, load time, execution time, and process in memory. So the flow chart for this is as follows. We start, initialize some data, create the socket server. If there's no error, we set the socket to port 8080. Again, if there's no error, listen for connection. And this is where we're going to wait until there is a connection from a client. Again, if no error, we accept the connection. If no error, read from the socket, print the message to the terminal, send the message back to the client, print the status, and then exit. Okay, and that's what we just saw. So scenario 1, provide method to service IO request with implementation details. So this could be the implementation of the socket listen functionality. This program provides a method to service an IO request. The user call is listen, and then the file.
Anthony,
file,
you're reading a lot of text, and I asked you not to do copy pasting. You still went and did copy pasting.
But I wrote this. I didn't copy paste it.
But you couldn't develop some diagram. I think you mentioned that it was you copied whatever it was before. But in any case, so I'm looking at time, and we have one more person to do presentation. Go ahead. So where are we going to go? You're this program provides a method to service IO request. So listen, I mean, there is a diagram that you could show this. Because the rest of it is you have the code. I have to look what it is, but okay.
I mean, this is how
you're losing context. That's what I'm trying to say. You're losing context but
my intention was to do it like this.
Because you could just explain the code, That's you see there is a listen system call. That's what you're trying to show, right?
Yes.
And that listen system call is got that's the parameters, the server, file descriptor, and 3. So, you could have shown, the whole entire network, this how to build the network server, right? You could have shown it in one diagram. But go ahead.
Okay, so the user call listen 3 puts the system into interruptible sleep. When the IO, the process is on the IO wait queue. When the interrupt comes in, signaling that the socket has a connection, the process will be put back into the running or waiting to run state, and the scheduler will pick it up again. So scenario 2, compile time, load time, execution time. We can create a system to do late memory binding when linking programs. So this is a program that is memory bound at execution time. It'll be linked with system libraries it calls in its memory space group created when it started. This is dynamic linking. The thing I wanted to show is that we build this program with GCC program 3. These are the headers that we're including. If we run LSOF, which lists the files that this program is referencing when it's running, we can see that there are these two system libraries that it's referencing in its memory space, libc and ld. So the system is calling these libraries at execution time.
Could you go, so the scenario is, and you decided to go through the compile time, run time. There's also a diagram explains that, okay? And then you copy paste code instead, right? Okay, so continue, please.
Okay, process and memory. So we can design a program loader that populates the PCB and handles memory loading. A process in memory is a program that has been loaded into memory and is able to execute. When a program is executed, the process must be loaded by a loader. And as mentioned above, this process is memory bound at execution time and is dynamically linked. Process in memory will have a memory structure consisting of sections for stack, heap, data, and text. The process will also have a PCB created for it, as mentioned earlier when discussing process states. This will keep track of the state, PID, PC, registers, memory space, open files, and more.
Okay, Anthony, I like to ask you to continue.
To the next one.
Because, yes.
Okay.
Because you're just reading text.
Yep. This program uses a pipe. It writes 2 messages to a pipe and then reads them back. If I run it, we'll see message 1, message 2. Here's the flow chart. Start, create pipe. There's an error exit. Write 2 messages to pipe 1 and read 2 messages back on pipe 0.
Okay.
We talk about pipes, MMU, and memory management and page table. This is also built with pthreads and LRT. Okay, so pipe, half pipe, full pipe, duplex. This program uses an ordinary pipe to send and receive messages. Pipe is a simple form of IPC supported by the kernel. Program starts by creating an in array of 2 and then passes it to the pipe call. So the pipe call is pipe with the array we've created. The program uses full duplex pipe. It writes 2 messages to pipe 1 and then reads them back on pipe 0. Let's load this over. The user space program is able to interact with the pipe with standard read and write calls after displaying messages the program exits. Okay. Scenario 2, what is an MMU? So we can create an MMU system that utilizes a TLB. An MMU is a memory management unit. MMU is responsible for translating logical addresses the program used to the physical addresses stored in RAM. I mentioned earlier that these programs are dynamically linked. The MMU is one of the components that makes this possible. The MMU in use for this system uses a translation look-aside buffer. And then I have, again, there's a diagram of the CPU, the page table, the TLB. One thing we can do is create a function to do physical address lookup. So if we pass in a logical address, this system can check if the address is in TLB, and if it is, return it. Otherwise, we have to reference the page table to look up the address and get it that way. Okay, scenario 3, memory management. Pages, frames, page table. We can create a component to allocate free frames. Continuing this memory discussion, the memory is mapped from logical memory pages to physical memory pages. Paging allows memory pages to be in memory in non-contiguous locations. When the process is loaded into memory, a number of frames from the free file table are taken and associated with the program pages. Okay, so for this, I've shown a function called get free frames, and we can pass in the number of frames we want. Get free frames will set a status. And it'll then check free frames list for each number of frames we want. If we have a frame, we can push it onto the frame table. And they'll then return the status, which is the number of frames we've associated and put onto the frame table. Okay. Program 5 is a program that creates 2 threads, and it also uses a mutex to synchronize between them. One thread is going to write, being the producer, and one thread is going to read, being the consumer. We'll see producer, consumer. The message written is hello world, and the flow chart shows this. We start, initialize a mutex, create 2 threads. If the thread is the consumer, it locks the mutex, opens the shared memory space, maps the memory space, prints a message to the shared memory space, unlinks and unlocks the mutex, and goes to thread join. I'm sorry, I said that backwards. That was the consumer. If it's the producer, it will open right to the message space and close. And the items I'm going to talk about are the shared memory, IPC communication synchronization, and CPU switch from one process to the next. Okay, so shared memory utilizes kernel memory functionality. In this program, the producer, the shared memory is created by the producer.
That's the code, right? That's the code.
This is walking through the code, yeah.
Yeah, we don't need to do that, right? Could you continue, please?
Okay. Scenario 2, well, this is going to walk through the IPC code too.
Okay, okay. You have the code on the left, you just ran it.
Yeah.
Okay, so this picture, what is it this picture does?
So I created this diagram. This shows CPU switching from one process to another. So in the case of needing to do a context switch, we'll say the first process will be our process here. If it's running and it's interrupted, we're going to save the state, meaning the registers, the process counter, and everything else, to the PCB. The PCB for the next process coming in will be loaded. It'll execute until it finishes or there's an interrupt, and we will save the state of this process and then reload our original process back and continue executing. And I have some text. You want me to not read it?
Go ahead.
Okay. We discussed swapping dynamic loading previously. These enable the process to be moved in and out of memory space. The process will support being swapped in and out of running state. This is known as context switching. As this process runs, it is
just explained. I understood it, but you just explained the diagram.
Okay.
So I think you walk through this.
Okay.
You just explained the diagram. So
okay. And I have
the diagram. We don't need to, right?
Great. I'll forget that. So I have a snip of code that could be a mechanism that runs a process called run process. It gets past a PCB. It'll initialize a stat. It'll first load the values from the PCB, meaning the registers and data. And then while there are no exceptions, it'll run the process. When there's an exception and we get interrupted, it'll save the state and then it'll return back to the scheduler that is controlling this. Okay. So that was all the programs and the sections. The last thing, just discuss what is entailed in 5 of these programs running at the same time. So we would need to support task switching that we saw above. The PCB will need to be able to be loaded in and out. We will have IO queues for each of these. Each of these programs will touch an IO queue. Each process communicated with the terminal. So at some point, a process will be waiting on a terminal IO to finish. Some programs wait on keyboard input. One waits on socket input. So it's a different queue. Process loading memory. Each process needs to be loaded from disk to RAM. And each process will have its own memory space. It's possible that memory held by one of these programs will be needed by another. So the process memory may be paged out to a backing disk. There'll be schedule requests. Each of these processes will be awaiting execution in a queue at some point. Caching, it's possible that these programs running concurrently will cause some cache conflict with each other. Protection security, each of these processes operates in its own memory space. And then I just described what it's probably actually like to run on the system. In reality, these programs are small and short-lived. With the exceptions of one of these that are blocked by some sort of I/O, they should all finish quickly. There are more than enough cores for each process to have its own processor. I'm not sure how to.
Anthony, I have to. I think are you towards the end? You finished.
This is it. I'm done.
Okay. What I want to say is that in this last piece, the consideration, you are very generalized. Okay. What I like you to see is work for you. What you have 5 programs. First of all, clean it up. Okay. Because is your work, is a presentation. Go. What you need, you can simplify things much better. You have the source code. You have the flow chart. You need to, the considering 5 processes, you need to look at what you defined as the scenarios. And then what happens? You need to make some design decision. Not generalize. Yes, there is a task switching, there is an I/O queue, but those are your programs. You defined 5 programs. You need to make some decisions. Say, my process 1 is going to take this, and time slice expires. So I have to do time in switch contacts, and then think of and then contact switching. You showed something about that, okay, as a thing. But whatever you did in 5 programs, you need to bring some context to it, because all of this is going to apply to every program in the world, okay? But you need to bring some context within your 5 programs, okay? And so that's one comment. And the other comment is clean up your presentation in terms of so much text. You can, work on it and present in diagrams. Just draw it on the page, and that should help.
Okay.
So that's my recommendations. And you may see this problem again. So if I see the same thing, I like to see better work. Okay. So work on consideration of all those processes and clean up the work.
Okay.
And that's my recommendation. Okay. Okay. Thanks a lot. Take care. Who's the next? Last one is Pratish.
Professor. Yeah.
Pratish, could you just start, please?
What do I need to do with this?
Okay, everyone, you need to work on this. And
No, I'm sorry. What do I need to do with the Zoom? I don't know how to
okay.
command away.
What I wanted, let me, could you go to, you need to go and make you are the host right now. Oh, I am the host.
It looks like he's got it.
You don't need to do it.
I have the access.
It's all good. It's all good. Okay.
Can you see the screen? Can you just confirm me that?
Yeah, we can see it.
Yes.
Okay. Okay. So can I start the presentation?
Yes.
Okay, thank you. Hello everyone. So today, I would be going over 5 programs that I've selected in OS and to build a particular operating system. So I would go over all the programs first at the start, and in the end we can see the device drivers and how we run all these 5 programs in an operating system. And I will just give a short design of the operating system. So my first program for today is multiprocessing IPC using pipes. So as you see on the left, there is a flowchart given of the code that I have written. So basically, what I do initially is I initialize the file descriptors. And then once the file descriptors are initialized, then I create an unnamed pipe. from that particular pipe, I go and create the child processes. Once like the child process one, the child one has finished the execution, it goes back, it exits its execution and goes back to the request goes back to child two, and it executes the read request, and it does it work, and then it exits. So how does this actually happens is like they both of the child are using the shared memory to read and write. So in this, like a synchronization is done like like at a time only one particular child is going and reading the shared memory and not the second one. Like I can go, we will go further in the scenarios like how actually this is happening. There is a small diagram over here which shows like how actually the pipe operation works. So first, like my actually command is like how we will get like a list of files and number of files in a particular directory. So that's the main output of the program. So you can see there are actually 10 files in the directory, and you get the output over here as 10. So here what it does, like ls commands list all the files, and we have a pipe operation in between, and wc -l, what it does is like it counts the number of files in the directory. So I have three scenarios to cover on this particular program. So first scenario is about the program process creation, process address space for both logical and physical address. So basically first what we do is like this is a small pictorial overview of what actually the process creation, process address space, both logical and physical means. So basically when we have a program is loaded in the kernel, kernel loads the code into the virtual memory and allocates the space of the program variables and sets up the data structure to record various informations about the program. For example, let's say the parent process creates multiple child processes, as we saw in the a flow chart over here. Like the parent, this the create main pipe, let's say that's the parent process, it creates the two child processes, and once the child processes are created, the individual arguments are passed like ls and wc. The fork system call is used to create the new processes in this particular program. In order to keep the process synchronized, the parent builds a pipe using a pipe function before creating the child processes. So that's about the process creation and the logical and address physical addresses. The second scenario is the preemptive and non-preemptive scheduler in this. So basically why this is selected is like just because like from kernel's point of view, processes are fundamental entities that it allocates the system resources. So in Linux, it uses preemptive multitasking. In system, the rules governing which processes receive uses the CPU core and how long determine the process scheduler rather than allowing the processes. For example, let's say in our program, each child inherits a file descriptor that we have in the code that is pipe FDs, the file descriptors that we have initialized for read and write operations of the end of the pipes, and closes the descriptors once it has completed the operations. Like here you see one child is created for writing the data in the shared memory, and another one is created to read data from the shared memory. So individually, each of them performs the operation and it exits that particular thread. And the next scenario that I've taken is like of IPC communication and synchronization of processes. Like we see, like we have a main process that is running, and there are two child processes that are created. Let's in our example, there are two child processes that are created that are going to the shared memory and reading the data. Let's say if we don't have the synchronization of the processes, so what will happen? Like both of the thread child processes will go and like it will go and perform its operation, which will result in a race around conditions, which we don't want it to happen. So that's why I have taken this scenario, and synchronize of the process is handled in the program. So Professor, I have shown the output of over here also. So you want me to go over the program?
Prayesh, could you go back? Just then come back here.
Yeah.
You did good. Okay, you did good. But I have a few comments. Go back. Could you go back down, down, down? No, I mean the other way. Yeah.
Okay.
One thing about synchronization.
Okay. The synchronization
Yeah,
or
this one. This one. So this is your third scenario, right?
yeah, that's third
The
scenario.
only thing missing here, you didn't say IPC in the context of your program.
Yeah, so Professor, I've covered the IPC communication in further slides as well. So it was the full bullet point. So I wanted to more focus on the synchronization of processes because that's what my program is mainly concentrating on.
Yes, but in terms of presentation, you need to show that.
Yeah.
All you're showing is that you're showing message passing IPC and the shared memory IPC.
Yeah,
your
so in
synchronization,
further
you
slides,
need to
Professor,
select
IPC.
one. You need to select one and put synchronization around it.
Okay. So
You know
I
what I'm
think
saying?
like here only synchronization should come, you meant.
Yeah, no, because you're saying that these are two different methods of IPCs.
Yeah, got it.
Shared memory, one is message passing. But your
Okay.
context, in the context of your program, you want to provide an IPC. So you select one and you select one method, and then you put, then your next thing is synchronization. Then you say, I'm going to protect this method with whatever. You see?
Yeah.
I hope you know. I hope you understand what I'm trying to say here.
Yeah, Professor, I got it.
Just saying the word synchronization and then showing a graph, a diagram that doesn't relate.
Okay.
Please fix that.
Okay, yeah, I will
You
work
can
on
either
that.
switch, you can either message passing or shared memory, and then put synchronization around it,
Okay.
right?
Yeah.
Synchronization is needed when processes are either trying to access shared memory segment or trying to do access the message passing. Actually, message passing is different.
Yeah,
But-
yeah, I got it.
But yeah, okay, go ahead.
Yeah, so these are the three scenarios for my first program, and the second program is about like the sorting an array using a p open. So basically, like I would like to go over the flowchart first. So like I would receive a stream of characters for as a input words, which the user like the the end user's requirement is to sort that particular string of words that they are passing in the alphabetical order. So let's say we get input words over here. Once we get the input words, we create a file stream, which will like go ahead and like we create a p open with the write operation. So which we allocate over here to a pipe, the file stream. If the file stream, if the output of the p open is null, so we don't go in, we directly go inside and say there was an error in executing the program. If it doesn't fall into the error, then what we go we create a new file stream and we just read that particular file stream and get the output using the fputs and fputc command. And then we close that particular p open the file stream using the p close. So here you see the output of the program. Like I have given an unstructured unordered way of output. Like you see echo, bravo, alpha, charlie, and delta. And you see here the output that I got is like alphabetically sorted. So in this program, like I have covered three scenarios, which is one is like half pipe, full pipe, duplex, and the second one is CPU instruction execution cycle, and the third one is array of string pointers. So first, here what I've done is like we are getting a string of input. So the data is flowing from we are just writing the data and then reading the data. So here it's a unidirectional way of data that is coming on. So that that fits our scenario, that is half pipe. And in going further, like CPU instructions execution cycle. So in this, why I picked up this scenario is like, so the first I get all the instructions that are that the user wants to sort. So first all the instructions are fetched and the instructions are decoded then, and then the address the the read operation performs, and then the program logic is executed. So there is a sequential flow of execution. And the third is array of string pointers. So here, what I'm getting data. So here, here in the picture, it's like characters.
Let's try it. This is your third program.
This is my second program. So it's the
this
third
is the
scenario,
third-
array of string pointers.
Third scenario, right?
Yeah. Yeah.
You should say that so I can see it. Right.
Okay, so I have written over here, this is my third scenario.
Yes,
And-
okay.
Okay. So in our data that we are getting is like we are getting a string of words that we want to sort. So I would be using, let's say H is like hello over here. Then it is so it is stored in a array of string pointers. So which is the most beneficial data structure for using this particular for this particular problem. So that's my all about my second problem. And my third problem is,
Can you go back to this?
yes, sir.
You're using a string pointer to
Yeah.
present an array of characters, right?
Yeah.
What is the difference between this character pointer, string pointer?
So in string, let's
Something
say,
that is you have an array of 5 elements.
Mhm.
What is the difference within? Yes, you are pointing to the beginning of the address of the first character, and then you can increment that to get to the next.
Yeah.
But what I'm saying is that declare the character pointer string pointer equal to hello,
Mhm.
and then you can have another way, say character a string pointer subscript 5 equal to hello, right?
Mhm.
You can create the arrays in 2 ways. One is the pointer to character, and the other one is a character array with a subscript.
Yeah.
What
got
is
it.
the difference between those two?
So basically, let's say we create a string. So in the backend, like it is stored as an array of like array of character.
5 elements.
Array of character.
5 elements. Yeah.
Yeah. 5 elements of character.
So what is the difference between an array subscript of 5 elements versus a pointer to a character string?
So here the sixth element would be the null element, which will say that the string has ended, and that's the length of the string.
Yeah. Okay. No big deal. But what I was looking for is that when you're defining a pointer to a string, which is a pointer to character,
Yeah.
like you said, is pointing to the address of the first character. Yes. And then you can walk to increment the pointer to get to the next character and so on, right?
Yeah.
But the thing is that this is called, when you do define a pointer to character array like this is a read-only memory. That means you cannot change. If you try to change any character within the string hello, you're gonna crash. But if you have char not the start, just a string pointer equal to, a string pointer subscript 5 equal to hello, you can change that during your program. So with a character pointer string, you cannot change it. If you change, your program crashes because you're declaring it in a read-only memory part of the memory. That's what it is. And you cannot change it because it's only read-only. A change means there's a right, change it. And you can't do that. But you can change it if it's using subscript of 5. Okay, so go ahead.
Okay, yeah. Thank you, Professor. So the next, my third program is about reading and writing 2 messages. So in this program, like I've concentrated only like reading like 2 messages from the parent process and writing those 2 messages. So here, what we first do is like we create a pipe like previously, like you see over here, we create a pipe where the parent process first writes the message over here, and once the message is written, parent process forks the process from which the child process is created. So once the child process is created, it goes and reads that particular message that parent has given. So in this, like first the flowchart looks like create a pipe, then we create a child process. The parent process writes to the pipe, and like the child process retrieves the message from the pipe and writes it to the standard output. And this process continues until we reach the fork condition is like the process ends. Until that we can keep on continuous. So this is a piece of code that I've written, and this is the output that I've received. And this is a
in your first program, you also had pipe, right?
yeah. So for that,
What is
like
the difference between this and this one?
so in that, like a year we are we are writing a continuous message. So this is related to communication that happens between between a sender and receiver. So like this is like something like a producer consumer problem.
Yes, but you need to be more, you need to expand it to be more clear, you see? You just
Yeah.
said write and read two messages. So,
Yeah.
well, actually, you're showing the diagram. Yeah,
Yeah.
you're showing the diagram.
Yeah. So I will go ahead and like I will say the scenario so it would be more clear. Like.
Okay.
Yeah, so the scenarios that I've considered for this are like the process state, the process scheduler, and the PCB. So first is like either in the process state, what we do is like there are various states of the process those are like new, ready, running, blocked, and done. So first, either the process could write down the file descriptor, or it could read from the file descriptor. So problem here is like pipes are intended to be unidirectional. If both process starts reading and writing indiscriminately, there might be chaos which would occur. So that's about the process state. So here what we do is like we fork into child process and parent process. Then the child first the main program executes and the child program executes. Then it exits and it waits and then it continues further for the execution. So the next thing that I've considered over here is the process scheduler. So why I've considered process scheduler is like in for process scheduling in OS tasks that schedules the processes of different states like reading, various states like reading, running, and waiting. So here we have like two models, like one is the a running state and one is not running state. So when the parent process is writing like sending the message, so the child process is not running. So here the only the parent process is running and not the child process. So in this that's why I selected a process scheduler to be a scenario. And the next thing is like the PCB. So why I've created a PCB. So going further, like if I create some struct like a this is a two-way communication. So there might be this particular application might be extended, and if we are designing an OS, so there might be some like if we are going and developing a communication system, so we might have a large system created, and we might need to create like a n number of PCBs to keep a track of the processes that are being executed. So we will need a like a structure, a struct node created for this. So by PCB, a process management is that like it can access or modify multiple OS utilities, including those are involved with memory, scheduling, or input output resource access. It can be like said that the set of processes PCB give the information of the current state of the process that is being executed in the OS. So this might be considered, PCB might be considered in case like if we are building an OS and a communication system is being built. So in that case, we can consider PCB. So, and then next is like we have mutex. So for this, what I've done is like, sorry. For mutex, what I've done is like mutex for
This is what?
basically
This is the fourth
next
program?
program. Yeah, this is the fourth program.
Okay.
So why basically for why I have opted for mutex and what are basically mutex use? I would like to give a short description. So basically,
So I just want to go back to the previous one.
okay,
Okay, so in this case, go down. Yeah. So you have the process state, the scheduler. You bring some context within your program, within the flow chart. You know, because go process state next. Okay, because this is a generalized, right?
yeah,
You need to bring some context to the program that you selected. Go back to your program. Go back up. Your program is the create a pipe, create a context, you know. So you're creating processes.
yeah,
But then, yes, one of the scenarios, so what was the first one? I forgot the first scenario. And
the
then
process state.
process state. Because what you're showing next is just the states. But you need to bring some context within that program, your flow chart.
Okay.
Not
So
the flow
basically,
chart. Bring, from the flow chart, you created the scenarios, but you need to bring some context to the scenarios.
okay,
Because you went from program to flow chart, from flow chart to scenarios. But when you're describing scenarios, you're just talking generalized. Yes, it is a scheduler, it is the state, and then there is another one. So bring some context within this one page when you're talking about scenarios. Do you see what I'm saying?
yeah, I got it. I totally got it.
And just I want you to, the goal of this for you to think design. Okay, so you're talking about the state. So what is it going to happening? You're going from scenarios to describe state as a scenario. So what is the context?
So basically,
What happens? What are you doing in your program for this? What is the program does? It's hard to see, but you're forking, and you're creating a parent, a child, and then the child and parent do different things. Okay, so bring some context. I hope you know what I'm saying.
yeah, I got your point.
Yeah, just bring some context to those, because the rest of it is just teaching, right?
I just gave an overview. So here, what I did is like I gave an generalized
This
diagram.
happens to every process.
Yeah. So I generalized gave an pictorial overview of what process state is, and then I explained how it is implemented in my program that I've written.
But you said explain. Explain means what in program?
Yeah.
Somehow you're going from one page to another. The context is lost. Okay.
Yeah, got your point.
That's what I mean to bring some context to that. Because what's showing is applied to every process, right? Every process. So, but you selected that program and that flow chart and this scenario, so you need to bring some context to this.
Okay, got it.
How does the state change? How do the scheduler with the context the program works? Once again, you're generalizing the scheduler. Yes?
Yes.
Just bring it's fine, but you need to bring discuss it within the context of your selection. You have two processes, a parent and a child. Okay.
Yes, professor.
Bring some context. Go ahead next, please.
Yeah, so the next is the mutex. Like why we use mutex is to prevent the data inconsistency due to race around conditions. So here, what I have in my program, what I've done is like I've initialized the counters. So let's say I have a global counter that is initialized to 0. Let's say you see on the right hand side over here. And what my program does is like first it creates a thread using p thread _ create. and it passed the address of the thread and the null and the various parameters that are required in the p thread create. And once the thread is created, what it does is like it locks that particular thread, and it then operates on the it does operation on the global counter, so that why locking is done is just because to prevent like accessing that particular like there is no other thread who is working on that particular thread, and it is updating that particular, modifying that particular variable. So what we do is like we create a lock on that particular thread, and then we change the counter to 1, and then we again lock the unlock the thread once the operation is done, and then we go back to the function call, and like just say like my work is done, and we just say my thread 1 execution is done. Once after that we create a thread 2, it does the same process. So in the meanwhile, when the counter was getting updated, the thread 2 was logged, it was in a logged out state. Similar process happens for the thread 2, where it updates the counter to 2. So I would like to give a short overview of what will happen when if we use this particular mutex without mutex and with mutex. So in mutex, we see like we are locking and unlocking when the counter is getting updated, and in like without mutex, there is no locking and unlocking mechanism in the function. So what are the possible execution, like what will happen when there is no locking and unlocking, and when there is locking and unlocking. So here you see when there is no unlocking and locking, so initially the counters are 0 for everyone, and once the thread 1 updates the counter, it's updated to counter 1, and also the counter of the thread 2 also it can see the same thing, which is counter 1. But this is the scenario for without mutex, that is the lock and unlock functionality is not there over there. So in mutex, like we see initially here also the counter values are same, but when the thread 1 starts operating on the counter, it changes the counter value to 1, and in that particular in the same state, like the thread 2 is in the lock state, and thread 1 has the exclusive use of the variable counter. So you see there is no change of variable over here. When the thread 2 gets the access to that particular counter, so it goes and update that particular counter. So you see the output of my program using this particular functionality of mutex lock and unlock. So in this, like I have taken like a couple of scenarios, 3 scenarios. So first is the synchronization for the threads that is achieved by mutex, locking and unlocking. Next is the thread. I have taken an example scenario of thread state, and the third one is thread versus process. So I just wanted to differentiate what actually the process is and what are the basic difference between the two. So here you see in my particular program, thread 1 is getting executed. So first it acquires the lock, and like it performs some operation on that, and you see there is no progress on thread 2 over here, in which you saw there was no counter variable access for thread 2. So here we like there is no progress. So thread 2 is blocked for making any changes. Once the unlock is the lock is released, the lock is acquired by thread 2, and it performs its operation, and it after performing it releases the lock. So this is the basic flow of the program and how synchronization is achieved using mutex. So this is the overview of that.
Pratish, that is very good. Okay, and this is what I was saying in the previous program. Bring some context. You see, now you did that for this last one.
Yeah.
That is the context. You see, right?
Yeah.
Because you said my program is doing this, then I have a shared resource. It takes the lock, the other threads gets blocked. You know, you're showing that in the context of your flow chart.
Okay, thank you, Professor. And the next is the thread state. So initially, as you see in the program, like I create a new thread. where the new thread is created. So this is basically the life cycle of each of the threads. So once the new thread is created, it starts it process, like it goes into runnable state, and like it performs some operations, and once, like if there is some exception occurred, then the thread exits and it goes into dead state. And once it is completed with the operation, it goes into a non-runnable state, and it stops, and then the thread goes into the dead state. So this is the whole life cycle of each of the threads. So here we have like two threads, so this is the cycle that it follows.
This
uh,
is also relatively generalized.
yeah.
You need to bring context block, right? The state within the context block. You can, because you're talking about state, the thread state. So, process control block,
Yeah.
you need to bring that in the context,
Yeah,
because
got it.
the PCB has the state. Okay, go ahead next.
And the next is like, I just wanted to give an overview what actually the difference between the thread and process. So I've utilized threads in over here. So basically, what threads are individual entity of the programs that we which are executed in the program. And let's the program as a whole act like a process, so we can say that. So this is a generalized overview that this is the scenario that I fit into this particular thing. So we have seen the execution for the threads and how the counter is incremented and accessed by different threads. Similarly, in case of process, the synchronization can be achieved by using the fork we create between the child and parent processes, as we have seen in the previous programs. So I would like to go to the last program that I have for today, which is like related to memory allocator. So in this memory allocator, what I have done is like I have created a, a struct block which has various entities in it. So what basically those entities are, first is the pointer next, which is the pointer that points to the next memory block which is available, which is not available. It is basically pointing to the next memory block. The second pointer is like a second entity is the boolean, and which says is free. As a name suggests, like it will store these details about the next block, whether it is free or not free. So it will, if it's free, it will stay keep the boolean flag as true, and if it's not free, it will keep as false. And the next is like the size which is allocated in the memory. It will the that particular memory block is consuming, so that's the variable size. And the next is void star pointer, like memory address pointer. So what this will store is like the starting memory address from where the memory is allocated. So that details will be stored in the memory address over here. And then last you see S block, where we will be allocating the size of this particular struct. So that will be stored in the S block. So as you see, we create a metadata structure like this, a struct, as I went through. Then we create that particular struct, and then we allocate the memory. Like I have the inbuilt functionality that is created that will allocate the memory. So in this memory, like what data structure that I'm following over here is like I'm taking a linked list as a data structure, which will so the data that I will be storing would be in the linked list format. So it will be continuous memory block. Uh, so I would like to go over the scenarios and explain on each of them. So first is I would like to go over the file data structures. The first scenario is about that. As you saw in the previous slide, like I have created a file, a particular data structure which is used within my program. So similarly, like how the data blocks will be stored would be like block 0 would be stored in the memory. So this is like how each block will be stored. So and the structure that I had, which is like the similar struct file over here. So that's how the data would be stored. And I would like to just give an overview of physical and virtual addressing. So what actually the physical refers over here is like hardware address of physical memory, and the virtual address refers to the virtual stored viewed by the process. And only here the portion of address spaces that processes to use is loaded and the physical memory at a time. So basically here why I opted for this is like, as this is a memory allocator, so I thought like just going over the physical and virtual addressing would be beneficial over here. So I went and opted for this particular scenario. And the next is like free space management, that which I'm concentrating mainly on this. So as we had in our struct node, we had a particular variable which stored the information of the next available block, which like if it is free or not free. So as you see, we are storing each and every data over here. The grayed out blocks are like the data that is being occupied, and the fragments are the spaces. You can say like these are unused spaces. Let's just take an example. So like this block will store an information like the next block that is available is free. If a particular request comes to store a particular memory block in the memory, so it will just sequentially go and check the flag of each particular block, and if it is if the next block is free, then it will go and allocate. So that's about the free space management that I thought like would be helpful in OS designing. And then next I would like to this were the 5 programs and all the scenarios that I've taken in the program. So now the question arises, how will 5 processes run in the OS together? So this is a generalized overview of sequential execution of the processes, but I've created a small diagram over here where I have like 5 processes over here which are executing parallelly. And like for each of them I have taken various scenarios. For first 2 of them I have taken like IPC communication, like, and half pipe for second one, and for first one like I'm using logical and physical addressing. And for the third process, what I've done is like I've created a PCB block and a data storage, main memory data storage, as it is performing some sorting functionality and storing data in the main memory, which will be provided by the user. So that's the main memory storage that the third process would be using. And the fourth process where I'm creating various threads, like it's reading and writing program. So it will create have various threads for in the memory. And the last one is like I create a data structure which would be created and like we can use a struct file for storing the data like for a memory allocation thing. So this is like a small diagram that I came up with.
Pratash,
Yeah.
you did a good job.
Yeah.
But
Thank you, Professor.
so there were a few comments. Could you go back to the previous ones? In some of the presentation, bring some context. For example, in this one, and then the next one, space management.
Okay.
No, just bring some context with the. These are scenarios of your flowchart. Just bring some context in. Just, once again, you need to think, oh, this is possible thing. You can. I have 3 files, and I want to create, and excuse me. So I have 3 files. I'm going to scenario, in just imagination. I'm going to create one file. I'm going to have there is this one file that the operating system manages, right, for free blocks, right?
Yeah.
You're going to say, I'm going to have a file that is going to manage 10 files, okay? And each, I'm going to have, I'm just making it up. You can, you know, say 4 files, but each one has got this size, and I've got the block, right?
Yeah.
And so how many that file is going to take? You know, maybe 2 blocks, right? And then, so the bed maps approach is going to set 1, 1, right?
Yeah,
Right?
that's correct.
And then the third file is going to have some size you do that. So think of it like that, you know. And I'm saying that because it's important for you to see those details, right? And just think, very simple, right? You know everything, right? You explained it. The, you know, bed map, how to manage the free spaces. So now you need to imagine you know, some scenario with the context that, okay, I'm going to have, you know, 8 files, and then each one has this size. My block size is this. What is the bed map is going to go look like? Okay. Now I'm gonna have, then I'm gonna, after you design it for 8 files, then I'm gonna say, oh, I'm gonna create a file, the 9th file, right? What's gonna happen to the bed map? Actually, you don't need to do that. Every time you create, the bed map changes, right?
Yeah.
And you can take the status of the current bed map to see what the next, and then you say, I'm gonna remove a file. What's going to happen to the bed map? You see? So that's the comment, and you do this kind of imagination on any context, on any scenario that you need to provide some context to it. Okay.
Okay,
Is one thing is okay to know what the algorithm does. For example, bed map algorithm, you know, if it's, you know, taken or not taken, right? But if you think about it, so what is it, how I'm going to create the bed map in a small scale, okay? And that gets you just, because that's what the operating system does. Okay, so that's one thing. And then, and do just walk through the scenarios and provide some context, the ones that you did very good on some of them, with a good context. So just take those as an example. And then what I just said, an example for fragmentation, free space. Okay, so then you go to the last one, the last thing. Could you go? Okay, so this is a good one. You maybe probably get, but the idea here is that you have 5 programs and you create a flowchart for each one, 3 scenarios for each one. Now you want to bring them in.
Yeah.
This is, you brought them in, but in a general sense, okay? And I don't want to make it difficult, all right? All I want you to go back to those programs and scenarios and build how the operating system is going to provide managing these different programs, different scenarios. And then you basically can take this one and just expand on it. But this is, nobody did like this. You're the only one that did approach. This is what, but expand on it, you know, go back to those programs and scenarios and then build this better. Okay?
Okay, Professor.
Yeah.
Yeah.
Listen, folks, thank you so much. What I want to do, ask you, is that I wanted to work on my recommendations, and I made recommendations to each one. Make this better, and then I want a package of everything. Your final exam is next Friday. It's going to be around 2 hours, and I'd like to have this by Wednesday. Okay, I want to see if, you know, I want to give you more time to work on my comments, and then I'd like to see a package everything, send it to me, and then the last thing for you is just take the final exam. So 10% of the final exam is going to be based on your midterm. And then when I said 10%, it could maybe 15%, you know, it's hard to, but 85 to 90% is going to be everything after midterm exam. And that includes, you know, just, the lecture notes and the homeworks, okay? You're not going to have any note sheets on this exam. I don't rely in just memorization. If there is something that you need to, I mean, there is general memorization, there is specific memorization. If there's something specific, I will provide you. But mostly, I want to see you mastering this subject, okay, of the operating system. That's what I want to see on the final exam. You've done, you know, a lot of work, hard work, and I hope that you learned a lot from this. Okay, so that's my story for today. Thank you so much, folks.
Professor.
Thank you, Professor.
Thank you, Professor.